Okay, so let's see. Do you see the screen, Rahul?
Yes, sir.
Okay, very good. Do you see the pointer?
Yes, sir.
Okay, perfect.
Actually, I was not audible earlier, I guess.
So we are eager to hear from you today about the graph signal processing.
Yes, indeed. Do you like me to start? Or
So we'll wait for a minute, and then Suyud Mukhopadhyay sir can give the introduction, then we can start.
okay, very good.
So Rahul, please let us know if sufficient attendees have joined.
Okay, sir, I think we can start now.
Okay.
Hello, Suyud sir.
Yes, just a minute.
Over to you, sir.
Okay, let me welcome Professor. Professor Dimitri van de Ville. He is PhD from Ghent University, Belgium, and he has done his postdoc from that Ecole Polytechnique Fédérale de Lausanne, that are more known as EPFL in Switzerland, and under Professor that Mitchell Unse, that he did his postdoc, and eventually he has joined that University Hospital of Geneva, Switzerland, as a professor, and later he also became the professor of EPFL also, and presently he is editor of IEEE signal processing and a new journal, that Neuroimage, from that last year 2020, and he has a lot of publication, and he is also that founding chair of EURASIP Bioimaging and Signal Analysis. So he is a very knowledgeable person and good at research. So, and we would like to hear from him about that graph signal processing. So request Professor Dimitri that if you please deliver your talk.
Thank you very much, Sudipta. Thank you for the kind introduction, and also for Rahul for the invitation coming out of the student chapter at the IIT Kharagpur. I really appreciate. So it's actually nice to mention that this is the first distinguished lecture I'm giving. So it's really a pleasure to give it to a student branch of the IEEE Signal Processing Society, because I think that's one of the main possibilities of outreach that this IEEE program gives. And so I'm happy that you can benefit from this. During the talk, feel free to put any questions under the Q&A, and then we can answer it afterwards. So I hope you can all see my screen. I think that should be fine. In case of any issues, don't hesitate to interrupt me, Rahul, or any of the other panelists. Okay, so I will talk today about graph signal processing and how that can be used for computational neuroimaging. But before starting with that, the IEEE asked me to quickly introduce their society and their activities. And so I'm going to show you a couple of slides just that they have actually asked me to share with you. I'm sure you know most of it already. So the IEEE Signal Processing Society is actually the first society within the IEEE, established already in 1948. So it has more than 70 years. And today it has more than 18,000 members over 120 countries. As you know, the purpose is to support research by joining resources, by organizing networking and events, and of course, above all, by supporting student activities, even if today that is obviously a bit harder than before, but still. And so I guess all the attendees today joining in from the IIT Kharagpur, they know, of course, for which chapter they are part of, but there are really many chapters and branches over the world. And if you like to look up, maybe if you're from elsewhere, what is the closest one, you can use the locator as part of the SPS website. I also like to mention just about the membership. Something that is recent is that today you can get an essential package membership if you're a student for basically $1. And that's new with respect to a couple of years ago. If you like to have the subscription to the digital library, you need to go to the preferred membership package, which is a little bit more expensive. Although for some countries, IEEE has now introduced a reduced membership fee, as you can see here in this slide. So it can go either to $11 or to $4. And that is all for the essential package that was mentioned before. So IEEE Signal Processing Society also has an app for iPhone and Android, and it tries to keep you updated using the social media like Facebook, Twitter, and so on. So if you're interested, feel free to visit those websites or to follow them on your social media account. So with no further ado on the SPS, I think it's now time to start the talk. And let me start with a brief overview about what I like to present you today. So first of all, I will give you a quick introduction, a quick update, maybe if you're not from this field, about what the so-called network neuroscience has already done for us in understanding the system level organization of the brain. And one of the important and still open questions is how structure and function are basically coupled with one another, how they are supporting one another. And to better address that question, we will build upon an emerging tool from the signal processing community, which is graph signal processing. And to be able to do that well enough, I'm going to introduce the basic theory of GSP. So we will look into how we define a graph shift filter, how we look at the spectral domain, how we then implement filtering in the spectral domain, and why the graph Laplacian is playing such a central role in this whole scheme. And then we will apply it to human neuroimaging data, first of all by applying it to resting state fMRI, which will be new ways, which will propose new ways to process spatial activation patterns, and also quantify this, what we will call alignment between brain function and the underlying structure. And then I will quickly show you some extensions to high resolution brain graphs, as well as a final outlook. So let's get started with how traditionally network neuroscience using data obtained from magnetic resonance imaging would be has been established today. So typically, if you like to analyze the brain under the perspective of graph theory, you would start off by choosing your favorite brain atlas. This is basically a porcellation that divides the brain into a number of brain regions, and many different atlases of different resolution are available. But in the end, you're going to use that atlas to define the notion of a node. So each of the brain regions defined by the atlas will correspond to a node in your graph. And then typically you have two ways of coming up with the edge weights. Either you rely on diffusion-weighted MRI, which is a kind of structural information that provides you with orientation within the white matter and can basically allow you to figure out, using tractography, what are the dominant orientations in terms of axonal fiber bundles between different brain regions. And that can be translated into edge weights of your graph, which if you do that for each pair of regions, you end up with an adjacency matrix, which you can consider as a so-called structural connectome of the brain. Or also, if you like, a wiring diagram of the brain. So that is the structural view of the connectome, but you can also look at the functional connectome, which you can obtain by looking at so-called resting state fMRI for a couple of minutes. So you get for each of those brain regions a time course which is representing spontaneous fluctuations of brain activity. And you can then apply Pearson correlation to compute the correlations between each pair of time courses to end up with your edge weights between the same nodes as we had before. And now Pearson correlation can be interpreted as an amount of information sharing, which if you put that all together in another adjacency matrix, you can consider this as the functional connectome or the communication diagram of the brain. Now, this has been pretty much established in the field. Obviously, it is still being improved and imaging technology is also proceeding. But one of the main fundamental questions that is still very much open is how do we actually integrate information from structural connectivity with the one from functional connectivity? And different approaches have been proposed. First of all, a whole class of techniques have been proposed, basically building upon correlation between structural and functional connectomes, or with somehow trying to use the weight of one onto the other, of which I'm mentioning here a few approaches at the bottom. Another type of approaches has been driven by so-called neural models. These neural models, they take a structural connectome and they're going to use that with some knowledge about how brain activity at an individual node can be generated to basically simulate brain activity, which you can then use to get a simulated functional connectome, which can be compared with an empirical one and can be used to optimize the parameters of your neural model. Another type of approach I like to mention, because it has some similarities in the results with what I will show you later, are the so-called brain gradients or connectopies, which use typically functional connectivity to come up with a gradient map of the brain. And this can be, for instance, the leading eigenvectors of the graph Laplacian, but graph Laplacian based on the functional connector. Yet another class of techniques is based on control theory and network communications, using the structural connectome as a starting point. Or finally, and closest to our work, are the so-called connectome harmonics, which are using structural connectivity to derive, through the eigendecomposition of the graph Laplacian, so-called harmonics of the brain. And that is, in the first step, very close to what we will do with GSP. Okay, but let's take a step back now and go to the more signal processing side of things. And let me introduce to you the basics of graph signal processing, at least for what we will need it for our application here. So to set the stage, we're going to consider in this work undirected weighted graphs defined by their set of nodes and their set of edge weights. And we're going to consider capital N nodes. So in that case, we will have a symmetric weighted adjacency matrix of size n by n, containing, of course, the edge weights, which I will denote as the matrix capital A in bold. And then I can derive the diagonal degree matrix, which, of course, on the diagonal contains the total, the degrees of every node. Now, that is the definition of our graph. For our graph signal, we're going to introduce a vector of size of length n, which is attributing to each node a value x subscript I. So you can represent the graph signal as this weighting of the individual nodes. So next, I will need to introduce a graph shift operator. Now, in general, a graph shift operator S will be actually an n by n matrix, which is representing a linear operator acting on the space of the graph signals. And in the end, it is shifting, but by shifting, I mean it is linearly transforming the entries of the input graph signal into linear combinations of the shifted graph signal. And so typically we use operators that only involve direct neighbors of the graph. So one choice of the graph shift operator can be the adjacency matrix A, but typically one goes with the Laplacian matrix, which, as you probably know, is the degree matrix minus the adjacency matrix. Or if you like to go with the normalized Laplacian, you can go for the so-called symmetric normalization, which is normalizing out the degree distribution of the graph. And the very important notion we will need on this graph shift operator S will be its eigendecomposition. So we're going to factorize the graph shift operator S by means of its eigenvectors and associated eigenvalues, respectively vectors ui and eigenvalues lambda I. And the reason we're going to do that is because for the choice of our graph shift operator, and I come back to that in a moment, we will consider that actually the eigendecomposition of S is defining our graph Fourier transform. Or in other words, it is S that is inducing the spectral domain for spectral analysis of our graph signals. And you can see this more clear by these two very simple equations. If you have a graph signal X, we're going to consider its graph Fourier representation X hat by doing the inner products of the graph signal X with the eigenvectors of the graph shift operator. And of course, since this is a unitary transform, we can get back, reconstruct the original graph signal by recomposing with the basis vectors defined by the eigendecomposition of S once more. And what is very beautiful is that if you're now going to, for instance, apply the graph shift operator to a graph signal, you can interpret this in the spectral domain as follows. So you're going to apply S to X to have your graph shifted signal. And this can be interpreted thanks to the eigendecomposition as a weighting of the spectral coefficients of our original graph signal X. And the weighting is done by the eigenvalue of the graph shift operator. And it's actually this principle of spectral interpretation that can be further generalized, and that leads to the concept of a graph operator that is shift invariant under S. And so that means that we can basically commute a graph operator that is shift invariant with S itself. So this identity should be satisfied, and it's very easy to see that this is always the case if we choose our graph operator H such that it's a polynomial of our graph shift operator S. And we only need to look at degrees up to n-1 due to the Cayley-Hamilton theorem. Very beautifully also, this general graph shift operator being shift invariant under S can be seen in its spectral representation, where you can very easily figure out that the spectral weights of the graph operator H are given by applying the polynomial to your eigenvalues of S. This is really very easy to show and a nice exercise if you want. And so that means that, again, we can look at the spectral representation of H being applied to a graph signal X by replacing H by this eigendecomposition representation. And if you now work out this as a function of the Fourier transform of a graph signal X hat, you can see that we are basically weighting the graph signal by these H hat weights that we have obtained as the polynomial applied to the eigenvalues. Let's maybe take a step back and just represent more graphically what all this means. Because what we've actually done is proposing a graph spectral filtering algorithm that solves the problem of shift invariance on a graph. Because obviously, since a graph can be irregular, that's the most difficult issue to tackle if you want to filter on a graph. And so the solution is basically to implement and to choose the filter in the spectral domain. So let's take the step back, and here we have a graph signal X in the original domain. We're going to graph Fourier transform it into the graph Fourier domain by applying our eigendecomposition of the graph shift operator. Imagine this is the Laplacian. So this is the eigenvectors of the Laplacian. We apply that to X to get the Fourier transform of X. And now we're going to apply our graph filtering operation by weighting those spectral coefficients with our with the spectral weights of our graph filter. And we're getting back into the original domain to get our filtered signal. So this, of course, reminds you to the famous convolution theorem. It's just like in classical signal processing, you can implement a convolution in the spectral domain. The big difference is that we don't have a regular convolution that directly links the original graph signal to the filtered graph signal. So basically, this is a very difficult mountain to get across. And it's still very easy what we actually did, because since everything is linear, you can easily come up with the matrix H that is representing this direct step going from the graph signal to its filtered version. And what you can see is that basically this matrix here, which is, if you like, the inverse transformed version of the spectral window of your graph filter, will contain in its rows the different impulse responses of your graph filter, and those impulse responses will not be necessarily shift invariant. So you don't get back to the stationary convolution on a general graph, but you still implement it in a very similar way as the convolution theorem. So to maybe explain this a bit more, let's look at the graph Laplacian of a very simple graph, which is a cycle graph that is representing a one-dimensional signal with periodic boundary conditions. So in such a case, we have a very easy adjacency matrix indicating just the connectivity of each node with its neighbor when we place all the nodes on a cycle. And we can compute, of course, the Laplacian of this as a matrix having 2 on the diagonal and then -1 on the 2 neighboring nodes. Now, if you look at the eigendecomposition of the Laplacian of the cycle graph, you actually find exactly the equivalent of the discrete Fourier transform. That is, you will find pairs of an orthogonal basis with equal eigenvalues by pair, and the vector will have an increasing frequency just like the discrete Fourier transform. So you see here is the DC coefficient with eigenvalue 0, and then here you have like two pairs, like a sine and a cosine with the lowest possible frequency on this grid, and then it increases into faster and faster oscillations. So in other words, you can interpret lambda, the eigenvalue, as the frequency, and u, the eigenvector, as the graph Fourier vector. And so you see that in the case of a cycle graph, the whole construct that I showed you maps back into traditional signal processing. Now, of course, the power of this is that you can apply it to a general graph, and what you still need to come up with is the choice of your spectral window for your graph filter. Imagine that you have a graph where this is the Laplacian spectrum, then I can give you a few prototypical examples. For instance, we could come up with an ideal low-pass filter. So we're just going to keep in the spectral domain the lowest frequency, the lowest graph frequency spectral coefficients of our graph signals. Or obviously, I could also go with an ideal high-pass filter. We could go with a choice inspired by diffusion on the graph and go with the diffusion filter. Or if you actually like to spectrally implement a Laplacian, you would choose as the weights of your spectral window exactly the eigenvalues of the Laplacian. And then you can make combinations. For instance, you can combine the Laplacian with the low pass to get a kind of a smoothed Laplacian filter. Now, there are two other reasons why the graph Laplacian is such an extraordinary choice to build graph signal processing upon. The first other reason is that the graph Laplacian is a very natural way to measure smoothness of a graph signal. Because if you're looking at the quadratic form of the graph Laplacian, you're actually looking at the differences between neighbors, squaring them and weighting it with the edge weight. And so that's, of course, a very natural way to measure the saliency of your graph signal using the graph Laplacian. And you can compute it in this very simple way, or actually in the spectral interpretation, you simply need to look at the sum of the energy of the spectral coefficients weighted by the eigenvalues of the graph Laplacian. And there's another beautiful reason that the graph Laplacian is playing a central role, which relates to graph partitioning. If you actually want to minimize the cut size, and let's think here for a simple bipartitioning of your graph, in that case, you can relax this problem. You can come up with a convex relaxation of this problem. And that will tell you that the solution will be given by the eigenvectors of the graph Laplacian. And the eigenvector with the smallest non-zero eigenvalue is very well known as the Fiedler vector, and it's giving you basically the solution, the convex relaxed solution to the bipartitioning problem. And that also explains why it is the basis of many spectral clustering algorithms that you probably have heard of in other contexts. So since about almost 10 years now, graph signal processing has been an emerging field in signal processing and has been used to generalize almost all of the operations we know in conventional signal processing to the graph settings. If you're interested in general in this topic, I would like to refer you to a couple of special issues, both of the IEEE Signal Processing magazine and also one special issue of the proceedings of the IEEE, where you can find a lot of information about these algorithms and methods extended to the graph setting. So now let's see how we have used GSP to be applied to human neuroimaging data. So the first work I'm going to mention has been developed by Thomas Bolton, who was a PhD student in the lab, and Maria Giulia Preti, who's a senior postdoc in the lab. And we start off by choosing the brain graph. So what do we consider as actually the graph? And the graph for us will be the structural connector. So the graph is based on the information of structural connectivity between each and every brain region of our atlas. So in this case, for the more technical side, we went with a pretty detailed atlas, which contained 360 regions of interest. It's the so-called Glacier's atlas. And then we derived the adjacency matrix using tractography algorithms, which are based on, which are using diffusion-weighted MRI data. And you end up with the symmetric adjacency matrix that we also normalized for the degree distribution. So that's the graph. Now, what will be the graph signal? That will be activation patterns that we extracted from functional magnetic resonance imaging and actually resting state fMRI data, which means you have about 10 minutes of resting state, meaning that the subject is in the MRI scanner, but he's just relaxed. He doesn't fall asleep, but he's also not processing a specific task. There are no stimuli. So we are really looking at spontaneous fluctuations of brain activity. And you can see here a representation in matrix form where every row is a different brain region and every column is a different time point. And the temporal resolution of this matrix is about 0.7 seconds. So we get a whole pattern of activity of the brain each 0.7 seconds. Now let's first look at how the eigenmodes of the graph Laplacian look for our choice of the structural connector. First of all, we start with the eigenvalue 0, which is, as you can see, basically the equivalent of the DC pattern. Since we have the normalized graph Laplacian, this is actually having some reminiscent degree distribution, but it's basically a flat pattern, the constant spatial pattern in the brain. If I now move at the smallest non-zero eigenvalue and its corresponding eigenmode, what you see is that it actually codes, if I may say like that, for the left-right division in the brain, which is in some sense the first geometry that is most important to represent if you're building up the eigenmodes according to the connectivity that the Laplacian is seeing. And if I go to the next eigenvector, you see that in this time, the geometry that is encoded is basically capturing frontal or anterior nodes versus posterior ones. And if I go yet to the next eigenmode, we see that we kind of get an interaction between frontal to mid areas versus posterior areas, but of the other hemisphere, etc., etc. So we basically built up the geometry of the brain with this information of structural connectivity. So now, given this graph Fourier transform that is exploiting the spatial connectivity of the brain regions, the first thing we can do is look how the energy of the functional signals is actually distributed on top of this graph Fourier transform. And so we're going to do the equivalent of an energy spectral density on the graph of our functional graph signals. And to do that, we're going to transform basically each column here of our fMRI matrix into the spectral domain. And then we're going to look at the energy of the graph Fourier coefficients, and we're going to average that across all time points for a subject, and then actually even look at the variability across subjects. So if you represent this information as a function of lambda, so the eigenvalues of the graph Laplacian, what you can see is that you have a kind of a power law behavior. So in other words, we have a lot of energy in basically the first few bit low frequency graph Fourier components. And then as you go to higher and higher spatial frequencies, the energy becomes smaller and smaller. So that's the first important observation, because it shows us that somehow the way brain activity patterns are expressed on top of these structural eigenmodes is respecting the natural smoothness of the brain in terms of its anatomical connectivity. And so it's not just that the function can do whatever it would like to do, it is respecting the underlying structure. It makes sense, but it's very interesting to see that this is empirically confirmed. Now, for the next steps in the presentation, I will also need to have a tool where we can, to some extent, randomize the data, because then we can test whether, in the statistical sense, we can test whether some properties can be really attributed to the empirical data, or they can be basically rejected based on a null hypothesis. And so the scheme I want to propose here is another generalization to the graph setting, starting off from the traditional but very popular Fourier phase randomization method. So just as a quick reminder, for the Fourier phase randomization method, one is using a discrete Fourier transform. And we have the traditional discrete Fourier matrix F here. And then on the Fourier coefficients, one is going to either permute the phases or randomize them, obviously maintaining Hermitian symmetry because we have real valued signals. But this can then be repeated many, many times. And each time you choose another permutation or randomization matrix, you get a new surrogate, so-called surrogate signal. Now, by construction, the energy spectral density of the surrogate signals will be equivalent to what you can measure of the observation. So in other words, the surrogates respect a prescribed covariance structure. Now, this scheme can be very nicely generalized, and this was work by Elvira Pirondini, who's now at the University of Pittsburgh, to the graph setting by replacing the discrete Fourier transform by the graph Fourier transform. And because we don't have a phase in the sense of complex values, but we do have a sign, we will permute or randomize the signs of our graph Fourier coefficients. And this can then also be repeated many times. Each time you come up with a surrogate signal. And by construction, these surrogate signals will preserve the energy spectral density in the graph sense. And this is a very elegant but simple way to prove this. If you actually look at the smoothness of your surrogate signals by looking at the quadratic form of the Laplacian, it's a one-liner to see that sign randomization will preserve the Laplacian smoothness. So this is a scheme that we will apply to our empirical data, just to show you the processing pipeline. So we're starting off with our data matrix. We're considering a graph signal, which is the activity pattern at a specific point in time. We're transforming this into the spectral domain. We're applying a sign randomization, and we're getting back to the original graph domain, which we can then repeat for all different time points in our data matrix. And you can repeat this for different randomizations, which will basically build a null distribution under your null hypothesis, which is in this case a null hypothesis that preserves smoothness according to your structural graph relation. Now, if for each column here, so for each time point of your data matrix, if you are using the same randomization matrix, in that case, it is very easy to see that you keep all temporal correlation properties of your data. Because, so if I do the, basically the covariance matrix of the temporal covariance matrix of my surrogate data set, so this is now number of time points times number of time points, you can see that this becomes independent of the randomization because my randomization matrix is squared, and thus every sign flip will be undone and will be equivalent to the time by time covariance matrix of the original data. So this is just another comment to say that this is actually quite a strong null hypothesis and preserving a lot of properties of the empirical data. So spatially, it's preserving smoothness, and temporally, it's preserving all dependencies between different time points. Okay, I need one more ingredient here, which is that I want to have a tool to basically undo the effect of the structural connectome itself. And for that, I'm going to reduce the structural connectome in the so-called configuration model. So that is a very simple graph that is conserving the degree matrix, the degree distribution, sorry, but without any preferential connectivity. And that can be obtained very easily by constructing this new configuration model adjacency matrix, which in essence is the outer product of your degree vector. And so it looks like you can see here at the right-hand side. So it has absolutely no preferential connectivity, but if you would compute the degree distribution of this graph, it is equivalent to the one at the left-hand side. Okay, and then one more thing I will need is our graph filters. And for that, we will go with a very simple choice. We will pick an ideal low pass and an ideal high pass graph filter. So it is defined in the spectral domain, and it is defined such that the cutoff of the ideal low pass filter on average contains half of the energy as we observe in our empirical graph signals. And that is about a cutoff at 30 out of 360 eigenmodes. And then obviously the ideal high pass filter will be complementary to that, and it will contain the 330 additional graph Fourier components. And so we will associate the low pass filter to reveal a notion of activity that is aligned or coupled with respect to brain structure, because it is following the dominant patterns of spatial smoothness as expressed by the structural connectome, while the high pass filter will be associated to a notion of liberality in the activity pattern or being decoupled, because it is basically expressed on frequencies that are not typically or not often used in empirical activity patterns. Okay, so now we have everything together to basically compute something interesting from our original data. So we're going to process our activity matrix, again, column by column, so time point by time point. And we're going to do graph spectral filtering by applying our low pass and our high pass filter to these different columns. So we start off, for instance, with this column over here. We transform it with the graph Fourier transform in the spectral domain. And we're going to do the ideal low pass and ideal high pass filtering on it. So we get two new filtered versions of our spectral graph signal representation. And we can reconstruct this into the filtered versions of our original data, one which we will call the aligned part of our data, and the other one that we will call the liberal part of our data. And as you can already see, suggested by this representation, the aligned one is obviously much more smooth than the liberal one in the spatial sense. And what Maria Giulia proposed is to now, once you have split your data into its aligned and liberal version, to compute a ratio for each brain region of the energy of the signal in the liberal versus the aligned port. So you can come up with other variations of this, but this is a very first choice that is really capturing how much energy in each region is basically redistributed in either the liberal or the aligned version. And this is called the structural decoupling index. So it is the higher this index, the more energy will be liberal with respect to the aligned one. And of course, we can then compare this for empirical data versus surrogate data, either surrogate data that has been generated using the configuration model or surrogate data that has been generated using the structural connector. So let me show you some results here. So here you see the representation of the structural decoupling index in log2 transformed. So basically at 0, we have no effect of being more decoupled or coupled. And at 1, we would have a doubling of the amount of energy indicating more decoupling, or -1 would be a half of the energy. So this is giving us a nice representation of this ratio. Now, if we look at the representation of the decoupling index for surrogate data that is generated on the configuration model, and of course, when we evaluate the structural decoupling index, we are evaluating it using the empirical structural connector. Now, what you would expect is that the structural decoupling index is very much decoupled, because the surrogate data doesn't take into account the preferential connectivity as we have it on the empirical structural connector. And that's exactly what we see. So the whole brain colors red, meaning that the decoupling index is indicating that all the signals are basically very much decoupled with respect to underlying structure. Now, something very interesting happens when we look at surrogate data that is generated using the empirical structural connector. So in this case, we are still looking at random data, but random data that preserves the natural smoothness of empirical data. And if you look at the structural decoupling index of this type of surrogate data, it gives you a very distinct pattern and clearly very different from what we've seen with the configuration model. So what you see is that we have regions, mainly visual, somatomotor, auditory, that are much more coupled with structure. And you have other regions like temporal pole, more frontal, orbitofrontal, which are more decoupled with respect to structure. And if I now finally show you how the structural decoupling index looks when you directly apply it to the empirical data itself, this pattern that you saw on the surrogate data is actually pretty much reinforced. So you see that now even more clearly, we have very strong coupling in the sensory regions, visual, auditory, somatomotor, and the decoupling is reinforced in the frontal regions. And so what this tells us is actually that there is in the brain a hierarchy, and a hierarchy that is well known from other types of analysis and even other types of measures. So there is a hierarchy in terms of organization between what is typically called the sensory or unimodal regions to the transmodal, or also called higher level cognitive regions. And so this gradient going from coupled regions to decoupled regions has been seen also in brain gradients directly using functional connectivity, or also extracted from measures of cortical microstructure, even gene expression, or neural temporal properties of neurons. So it is something that can be revealed in many ways, but clearly makes sense in terms of what is known about the hierarchical organization of structure-function relationship in the brain. And I think what is pretty cool here is that in this case, where we have realistic but random surrogate data, but that respects the smoothness with respect to the underlying structural connectivity, that actually this hierarchy is already mostly present as observed by the structural decoupling index. It is reinforced by the empirical data, but the main pattern is already there. And so that means that this property, this hierarchical organization, is something that very much relates onto how function is actually using structure. Okay, so it's really a fundamental property that cannot be easily destroyed if you do a kind of surrogate data generation as we did here, which respects thus the underlying structural connectivity. So maybe you're interested in what would be the difference between the structural decoupling index on surrogate data and on empirical data. And it actually looks like you see here. So we actually do see in the visual regions that the empirical data is somewhat more decoupled than what is predicted by the surrogate data. But that is not true for the somatomotor and the auditory regions. It's also not true for the parietal regions, neither the frontal ones. And I don't want to go too much into details, but actually this difference here is also something that has been observed in other studies. And it is described as a secondary gradient, which has been derived also from functional connectivity and genetics, and which highlights maybe the particular position of the visual system with respect to the visual sensory modality with respect to the other modalities. And this also actually shows you what are the regions that are found to be more decoupled, that are also most unique to each and every one of us. So in so-called fMRI fingerprinting approaches, these regions that are more decoupled have also been highlighted with respect to the ones that are more coupled, and thus less specific for individual. Just as a final confirmation that the hierarchical organization makes sense in terms of behavior, we've done an analysis that is very similar to the so-called Margulies study in 2016, where using a meta-analytic database, we have linked the gradient of the structural decoupling index to, as you can see here, so-called topic terms from Neurosynth, showing you indeed that we start off with regions that are coupled and related to sensory processes. And as we go to the decoupled regions, we go into really high-level behavior related to control, to language, to memory, to social cognition, emotion, etc. So showing again or confirming that this hierarchical organization does make sense also in terms of how you link it to behavior. Let me quickly check on the time. Okay, so I've been a little bit slow, but let me show you one more aspect of how GSP is interesting for neuroimaging, which I guess for signal processing people is very intriguing, because so far I have shown you brain graphs that have about 360 regions. And one challenge that has been taken up by Anjali Tarun in the lab, and also in collaboration with Hamid Bejat, who's at Lund University and now at Harvard in the US, has been to do the same idea, but on top of a very high resolution, large scale graph, where every node would not be a brain region, but become a voxel. Now, if you're going to do that at really state-of-the-art data, it means that you end up with almost 1 million of nodes, because you have almost 1 million of voxels if you combine gray and white matter together. But that's what we did. And so we basically used information from diffusion-weighted MRI to extract for each of those nodes the local connectivity, very much like people do tractography analysis, but without explicitly doing any tractography in this case. So we're basically just constructing the brain graph that encodes for the local connectivity on this graph. So the local connectivity between the voxels. And then you can compute still the leading eigenvectors using large numerical solvers. And what you can see is that, again, the eigenmodes of this huge Laplacian, they are different, but somehow conceptually similar to what we've seen before. So we have the DC component, which is basically kind of a constant eigenmode, highlighting very nicely the white matter structural connectivity in the brain. And if we look at the first non-zero eigenvector, we get actually first now anterior versus posterior division, and then in the one after that we get a left-right separation, and so on and so on. And then we get the combinations. Very similar to what we've seen before, but this time completely at the voxel level resolution. And so why would that be useful? Well, Anjali came up with a scheme where she said, we know that we can measure brain activity on the gray matter. So we're going to try to use the information of the brain graph to basically inpaint the activity onto the white matter, which in neuroscientific interpretation means that we want to come up with biologically plausible activation patterns on the white matter, given the measurement of activity on the gray matter. And to do that, you get to a very nice signal processing problem where we basically have a boundary value that is imposed on the gray matter. So that's the so-called fMRI Bolt signal, which is measured there. And you can see this as a temperature. And then through heat conduction, we assume that this temperature will evolve through the white matter, which is very much structured as encoded by the brain graph. So you can rely on the variation of formulation where you have a data fit and you have a smoothness. The data fit is only applied to the gray matter voxels, and the smoothness, of course, should hold on the full graph. And then using an iterative kind of diffusion step, if you like, or gradient descent, we can actually solve this, this problem very nicely. And I can show you a little video here, which is the inpainted version of fMRI activity. So in the original data, you only would see the signal at the border here, at the cortical surface, where you have the gray matter. But in this video, all the activity that is in the white matter has been inpainted, given these constraints of the gray matter in terms of function and of the white matter in terms of structure. And just to give you one example, without going into much detail, so in a traditional way, you could extract from fMRI this type of brain maps over here. And if you do a very similar type of analysis, but using this interpolated or inpainted version of the data, you get basically a map that looks like this, which is the same on the gray matter, but which now shows you which white matter structures have mediated this activity. And final example, and then I'm really coming to an end, is that we also have used this idea of diffusion, in this case, diffusion of activity that is expressed on the gray matter as a proxy for distance. And what I mean with that is we start off, so you choose a certain seat region and you construct a seat connectivity map. So this is basically looking at the functional connectivity between your seat region and each and every voxel in the brain. And that map is converted into the inpainted version using the algorithm that I've shown you before. Now, once we have this map, we're going to also take this initial seat connectivity map and doing a straight linear diffusion at different diffusion times on it. And we will look when is the in-painted map as close as possible to the diffused map. And the diffusion time for which this happens will indicate us what is the typical or the characteristic distance that we need to travel before we actually, our diffusion process becomes as close as possible to the in-painted map. And so that's why I'm saying that diffusion time is used as a proxy for distance, which if you convert it into a range map, as we call it here, a structure function range map, what you see is once more this hierarchy of organization that I've shown you before, but on completely different grounds, where you can see that the sensory regions, so the unimodal regions, they have a typical interaction distance that is very short, up to 5 centimeters. While if you look at the other regions like parietal, temporal pole, frontal, they have a typical functional interaction distance that is that's much longer. And so again, the same hierarchy shows up on different grounds and can also be confirmed with other studies. So to conclude, as a take-home message and as an outlook, first of all, graph signal processing is a very versatile framework, obviously not only for neuroimaging, but for many other applications. I think one of the beauties of it, at least for the operations that we have used, is that those operations are very principled and rooted in ideas from harmonic signal analysis. And that is something that is very attractive. Secondly, in terms of neuroscience, GSP has allowed us now in quite a principled way to reveal the hierarchical organization in the brain, to show this gradient from low to high level regions, to actually have a quantification of the function structural relationship in terms of activity that is more or less aligned with structure. And in the end, the last result, to also quantify the range of functional interactions of regions. So to give you a grasp onto what is actually happening at short range or at long range. And as an outlook, there are many possible extensions that you could envision of GSP and of GSP in this approach. So first of all, you could look at dynamics in time. We didn't do much on that so far. You could also try to build graphs that explicitly take into account the temporal dimension, so-called vector graphs or tensor graphs. You could reinforce the connection with biophysics and neurocomputational models. And last but not least, this is work by Milan, Rafael, and Thomas also in the lab. You could actually extend some of these ideas from the Laplacian, which measures smoothness and gradients, to what is called the modularity matrix, which relates to community detection. And in a way, you could actually go from a Laplacian-based GSP to a modularity-based GSP scheme. Okay, so with no further ado, let me thank you all for your attention and all the lab members who have contributed to this work. This picture is unfortunately from last winter, when we could still go out and have fun in the snow. It's a little bit more difficult, as you can imagine, these days, but we hope that we very soon will be able to do that again. So thank you very much, and I'm ready to answer some of your questions. So maybe I will stop sharing so I can see some of the windows here. Okay, so hello, I see there. Okay. Oh, sorry, Rahul, please go ahead.
Yeah, we have some questions. So the first question is how graph spectral filtering is different from common spatial pattern?
Yes, so it is different. I mean, Common spatial pattern is a machine learning tool from mostly used in EEG BCI setting. I mean, of course, you can say there is a certain similarity because it's also about matrices and in the end an eigendecomposition. But I would say that the concept of GSP is more universal than in common spatial pattern, where it's really focused on a discrimination task.
Okay.
And I can see the questions. So there is another one, how to make the adjacency matrix from the functional data. So if you start off with the functional imaging data, you would compute out of that the time courses associated to each region, for instance. And then you would compute the Pearson correlation coefficient between each pair of time courses. So if you have 100 regions, you end up with a 100 by 100 functional connectivity matrix, where each element is a Pearson correlation coefficient between the associated pairs of regions. And then is structural connectivity of the brain always an undirected graph? So by construction, it's actually not, because if you do tractography from one region from region A to B or from B to A, you typically do not end up with a symmetric measure. But almost all of the schemes, they symmetrize this initially asymmetric graph. From a more fundamental viewpoint, what we would like to have is directionality in the structural connectome, which is reflecting the real axonal directionality of the underlying fibers. And that is, of course, much more difficult because for that, you would also need to probably come up with new acquisition schemes that have the power to capture such much more complex type of information. Okay, but so there is, let's say, there is a symmetrization going on in the construction of the structural connector. And then I see another one in the voxel problem. Can you explain what local connectivity is used? So, okay, so the local connectivity is just the information from the local orientation that you extract out of the diffusion-weighted MRI. So like DTI, for instance, could be one type of local connectivity. And you're using that for one voxel, so for one node, to define the edge weights only with the neighboring nodes. So you're only encoding for the neighboring voxels connectivity through the orientation that you extract from DTI or DSI. So there is a question on optimized pipeline. I mean, there is, of course, a lot of work that I've kind of put under the corporate in a certain way. There is a lot of pre-processing going on before you get to the point where you can start applying, where you actually end up with your functional matrix with the graph signals that I've shown you. So you have many different steps of spatial normalization, realignment, cleaning the data, etc., which you should take into account. But today you can actually find pipelines that are proposed and that include all those steps. And so there is a question on whether the data is presented in the three-dimensional domain. So yes, that is the case. Everything is initially 3D. If you go with the ROI approach, kind of implicit, because a node is some region somewhere in the three-dimensional brain space. If you go with the voxel-wise approach, it is really 3D, I mean, very at the low level also, because the node is really employing, let's say, the neighborhood relations of a voxel are directly reflected on the neighbors of a node. So the three-dimensional aspect is even stronger present in that case. And so there is a question on graph feature attributes. I don't know what is meant, but I mean, it's true that there are many, let's say, other types of data that can be extracted, that are available, and that you could associate to either kind of edges or to nodes, and that you might use to answer specific questions. So I would say yes, but it depends what you like to do. So they might not be relevant depending on the questions you like to address. Okay, so I think I went through the questions.
Yes, based on the second last question, actually, I have one more question. As I'm a panelist, so I couldn't type in the Q&A section. So,
Oh,
sorry.
okay. Go ahead, Rahul.
Yeah. So as you actually showed some of the results of this brain connectivity. So like assuming I have a like video signal consisting of like 100 or 200 frames, and if I like take the ROI of each brain, like some part where the like, thermal changes has been happening. So how to like interconnect these thermal changes so I can find that there is some kind of change detection is happening in the ROI of the brains using adjacency matrix. Like we
Okay,
have got the adjacency matrix of all the ROIs of the brain. So how to find the change detection?
so you're referring to the temporal aspect, like when does brain activity change over time?
Yes, over time.
So I pretty much ignored this in this talk, right? So the most complex thing that we did, that I showed you, that we do over time, is computing the energy of the filtered time course of a region. Now, in other work, we've addressed more the temporal aspects of fMRI data, and actually, what you measure with fMRI can be modeled as having been convolved with what is called the hemodynamic response function. So it's basically a low-pass filter. So when you have some initial activity-inducing signal that is first being convolved with an HRF, and then you're measuring a noisy version of that. So in other work that we developed over the last 5 to 10 years, actually, it's already going to 2011 for the first work, we came up with temporal deconvolution methods that are regularized such that the activity-inducing signal, so the deconvolved signal, is realistic in neuroscientific terms. And this involves a combination of deconvolution with total variation. But this has been done outside of the graph setting. So you could indeed now think about extending the spatial graph that I've shown you with perhaps a temporal graph, and to combine notions of the temporal properties with these concepts of spatial filtering of the current talk. But we didn't do that yet. So for today, these are two different lines of research that have not been interconnected yet.
Okay, so on basically like if can we interconnect these or relate these using a covariance matrix or using this adjacency matrix? So can we interconnect like can we create a covariance matrix of all these images so that we can find a change?
Yeah, there are many methods that allow you to detect those changes, to deconvolve, as I mentioned. So I mean, you would really need to go a little bit deeper into the signal generation process. But yes, I mean, let's say if you like to put this into a graph setting, I think it would be possible to frame that into a space times time graph. But one important thing, this will of course be a very huge graph conceptually. So you will need to have a good motivation why it is useful to introduce the graph setting in this context.
Okay. Any more questions from the students or attendees or panelists?